In this project, Luigi, Emiliano, and I worked on a real-life water crisis problem, pump a tap, and try to give a solution using data from Tarifa and the Tanzania Ministry of Water available on the Driven data website. We start with the data exploration part, followed by data manipulation. After that, we will, or in the learn and algorithm part, we applied five models on the dataset: decision trees, random forest classifier, neural network, AdaBoost, and the additional method, which is multinomial logistic regression. For each method, we'll compute the accuracy, and based on that, we will conclude by choosing which one gives the best accuracy for the project. The aim is to apply different machine learning algorithms for classification and identify suitable learning technique to perform an accurate classification and draw insight on the dataset. Our goal is to predict which pumps are functional, which need some repairs, and which don't work at all. In the training dataset, we have 59,400 rows and 40 columns. Our target variable is named statue group, which has three categories: functional, non-functional, and functional needs repairs. Functional is the most frequent class with a percentage of 54%, followed by non-functional class with 38% and the last one is functional need repair with 7%. Our data is unbalanced because we don't have the same proportion in each category for the target variable. Since the part of pre-processing is very important, we took more time to understand and analyze our data before starting the modeling part. Here we have a visualization of some categorical variable. To understand the nature of features of the raw dataset. For what concerns the categorical features, 8 columns have more than 50 categories. This can create issues when trying some models or when converting with the one-hot technique. For the variable recorded by, this column assumes always the same value, hence it does not bring any information. Some other variables represent redundancy. For example, we can see extraction type group are same. Some values are merged together. We can keep one of them. Some other variables contain an empty values. We replace it by unknown, and it could also be replaced by the most representative class in the variable. For what concerns the numerical variable, except the variable ID, we have 9 other quantitative variables. We remark that we have many zero values in some variables. Some of them have no sense. Looking at the meaning of large amount of zero samples, it's reasonable to assume that they correspond to error or in the recording, for example. Now I let Emiliano explain the data manipulation and our first learning algorithm part.
Thank you, Youssef. I will now take a look at what has been implemented concerning data manipulation. First of all, let's look at what has been implemented concerning feature selection. As it is possible to see from this slide, many different features have been removed due to different reasons. The first one being the fact that some features were presenting a lot of unique values, more than thousands. So we decided to remove all the features that were presenting more than 50 unique values. It's recalled that the limit for the random forest to withstand unique values is 53. The recorded by column has been removed since it was only presenting one value, which was not providing any additional information, so we decided to drop it. Other columns were simply a clone or a copy of other columns, and thus they were redundant. The date recorded column has been transformed into the year recorded, month recorded, and day recorded. The blank samples have been replaced with the term unknown or other, and this happened to pumps permit, public meeting, and scheme management. Concerning the zero values in latitude and longitude, we decided to replace them with the mean of the positive values because Tanzania is not crossed by the equator nor the Greenwich meridian. So it wasn't making any sense that we had some 0 values. Concerning the learning algorithms, here is what has been implemented. We started with a decision tree with RPart, with the package RPart, and this is how we decided to split the data. 75% of the data was dedicated to the train set, while the rest to the test set. And here are the results. At the beginning, we used an extremely small CP parameter, which is a complexity parameter. And then we basically saw at what CP the relative error was at the minimum, was presenting the minimum value. So we found the best CP, which is in this area, and then we found the optimal number of splits of the tree. The increase in the accuracy is quite high. We passed from 74 to 78. The highest accuracy is 78.63%. Here is a representation of the importance of the variables. The quantity and the location were the two most important ones. Concerning the second model that we implemented, the random forest, the data has been split in the same way as before, and we decided to increase the number of trees from 1 to 150 to see the increase in the accuracy. And here again are the results. This is a confusion matrix, and as it is possible to see from this graph, which represent the accuracy against the number of trees, the highest accuracy is 81.11%, achieved with 147 trees. Again, the importance of the variables is represented here. And again, quantity is one of the most important variable, followed by the location, longitude and latitude. I will now give the floor to my colleague, Luigi.
Thank you very much, Emiliano. We will now continue with the last training model that we used as the single layer neural network. We have used a single layer with 6 hidden nodes with the same share of data set for training and test. In this case, we had to do one-hot encoding of the features, because that's how you can feed data to a neural network. It needs numerical values. We had the limitation with the package nnet for the number of weights. And we did not obtain really successful results in this case. The testing accuracy is lower than the other models. Furthermore, the model is not really able to detect the category functional needs repair. We can see that there is an explosion of the size of the input layer due to the one-hot encoding, while the output layer is composed by the 3 features that we want to identify. The additional models that we tested are an A2Boost and the multi-logistic regression. In particular, since we saw that the 3 models were performing quite well, we decided to consider A2Boost in combination with decision tree. And we used a very large number of trees, like 300, to try to increase the performance of our predictions. You can see in this graph that the misclassification rate, as expected, decreases with the increasing number of trees, since every tree is built trying to minimize or to correct the error of the previous trees in the model. We obtain a testing accuracy which is somehow comparable to the one of the random forest, however slightly lower. We can in general say that this is a good model. It might need some more hyperparameter tuning to perform better. So to conclude, we make here a benchmark of the models. We can see that in general, the best performing model is a random forest, which has the largest overall accuracy. However, as said, also the A2Boost decision tree model has quite similar overall performance. In general, the random forest is the best model and it's the one we select for our prediction because it has good classification accuracy also for the other two categories of functional needs repair and non-functional. We have seen that some models are not really able to identify this middle category of the functional needs repair. As mentioned, we have tested also another algorithm. There is a multi-logistic regression. We are not presenting it in detail in this presentation because the testing accuracy that we get is lower than our best performing models. So in conclusion, what we can say about the data set is that we have identified several redundancies and missing or corrupted values, which are difficult to reconstruct. We can make some insights on the features that somehow have a strong correlation with the output. In particular, the quantity of water available and the location are playing a strong role. The best performing model is by far the random forest and is the one we selected for the driven data competition. A2Boost is offering somehow a valid alternative. Maybe we should combine it with other models or improve it by increasing number of trees and performing some hyperparameter tuning. Thank you for your attention. You can see here our team more in detail. And yeah, I hope you liked our presentation. Thank you.